Okay, well, let's look a little closer at the regulation of an enzyme. The competitive inhibitor bound to or inserted and exited in and out of the active site. When it's in, true substrate can't fit in. When it's out, then it's a 50-50 or whatever, depending on concentrations, which gets into the active site next. Non-competitive inhibition or regulation also looks like what we see here above my head. Allosteric inhibitors or allosteric activators. An allosteric inhibitor, as you see over here on the left. Allosteric inhibition, the active site has a specific shape, the enzyme has a specific shape, until the inhibitor comes and binds. Notice here it changed the shape of the enzyme. Bound to it, changed secondary, changed tertiary, which then changed quaternary. Boom, different shaped enzyme. No longer has the correct shape, as we see here, of active site. So the substrate doesn't fit in. As long as that inhibitor's there, active site will not function. The wrong shape. But over here, when we look at the allosteric activation, the enzyme in its natural state is the wrong shape. The activator, right there, comes and binds to the enzyme, changes secondary, which changes the tertiary, which changes the quaternary, which means you now have an active site that is the correct shape for the substrate. Now, I have a problem with this figure. By having everything the same color, it gives students the wrong impression that an inhibitor and an activator would both go to the same enzyme and would both turn on, turn off the same enzyme. No. Most often that's going to be two different enzymes, and the two different enzymes are going to be using different methodologies to regulate activity. Now, you can also limit how much of the cofactor is able to interact with enzymes. Not all enzymes need cofactors. Some do, some don't. You go and you look at these cofactors. Look at it. Vitamin A, folic acid, vitamin Bs, and so on. These will bind to, interact with, and then cause the enzyme to get its correct shape. Correct shape now has a function. Same thing with cofactors. Cofactors have to be there for an enzyme to have a function. No inorganic ions such as iron, magnesium, zinc, well, that enzyme won't function. Great example of this, DNA polymerase. DNA polymerase has to have a zinc in there. Part of it's referred to as a zinc finger. It helps unwind and helps the polymerase associate with the double helix. If it's not there, polymerase can't function. As I stated, the coenzymes, the vitamins, are necessary. A lot of them we make, a lot of vitamins we make for ourselves. A lot of these coenzymes we make for ourselves. But there are the essential vitamins that you have to take in via your diet, whether it's plant or animal or, one of those one-a-day multivitamins. So a metabolic pathway, talked about at the beginning of this chapter. It's going to be a series of enzymes, as we see here. You start with some initial substrate, as we see right here, and Green triangle gets taken up by enzyme 1, turned into purple rectangle. Twist, tweak, cut, paste, remember? So triangle to A, this substrate A, or product A, or however you're going to look at this. A gets taken up by enzyme 2 and gets turned into B. B is going to taken by enzyme 3, twist, tweak, cut, paste, and gives us the final product. Remember I said metabolic pathway, step, 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 pathway through a garden. Well, step 1, step 2, step 3. Some of these pathways can be nice and short, just a couple of enzymes. Some of them could have a dozen or more. All depends on which pathway you're talking about. And then to add another level of regulation, competitive inhibition, non-competitive, allosteric, we also have what we refer to as feedback inhibition. The final product we see here will loop back and bind and deactivate the first enzyme or the second, somewhere up at the beginning of the pathway. Allosteric inhibition. By having enough substrate there, well, we don't need the pathway to function as much. But as the final substrate, the end product, goes down, well, you need the activity of that pathway to go up. Activity goes up, well, end product goes up. As it goes up, hits high enough, pathway activity goes down. And you get this balancing. Never truly on, never truly off. A balance effect within the cell.